Jai Hind everyone. In today's lecture, we are going to discuss about issues that occur when we cascade the dynamic Cmos logic and what are the possible solutions for that. This is the index. We are going to discuss about introduction to dynamic Cmos logic, cascading of dynamic Cmos logic, what are the issues that are associated with cascading, then the possible solutions, domino Cmos, Nora Cmos and zipper Cmos. These are the possible solutions for the cascading problems. Introduction. Dynamic Cmos logic is a design methodology for digital circuits which is an alternative to static Cmos logic, and there are certain advantages of dynamic Cmos logic over static Cmos logic, such as its primary goal is to increase the speed and reduce the number of transistors, leading to smaller, more compact designs. Unlike static Cmos, which maintain a stable output, the dynamic logic relies on the temporary storage of charge on the parasitic capacitance. So, this is the difference, one of the difference, and this charge on the parasitic capacitance is evaluated during a specific phase which is known as evaluation phase. Now, here we can see a diagram for a static dynamic Cmos logic. If you see this diagram, here we have a VDD, then at the bottom we have ground, and in between we have a PMOS and NMOS transistor and one pull down network. If you compare this circuit with the static Cmos logic, you will see the difference that in static Cmos logic we have pull up network and pull down network. Pull up network we can see here, this is pull up network and this is pull down network. This is the output, this is the VDD and this is ground. So, we can see there are two networks, pull up network and pull down network in case of static Cmos. But in case of dynamic Cmos, the structure is a bit different. There is a PMOS transistor and NMOS transistor at the top and the bottom, and in between there is a pull down network only. There is no pull up network. So, that is one of the difference in the structure. Now let us discuss about the operation of a dynamic Cmos logic. Here we can see there is a PMOS transistor and here it is the NMOS transistor which is driven by a clock signal, and in between there is a pull down network, and these are the inputs. This is the output. So, dynamic Cmos logic operation consists of two phases. One is known as pre-charge phase and the second one is known as evaluation phase. So, first of all, let us discuss the pre-charge phase. What happens in pre-charge phase is that PMOS transistor is on and NMOS transistor is off. This is on and this is off. So, what happens? If the NMOS transistor is off, the path from output to ground is open. So, output cannot discharge. but because PMOS is on, your VDD charge the output to logic 1. So what happens in pre-charge phase is our output is charged up to logic 1, that is to logic high or VDD. It happens in pre-charge phase, and during the pre-charge phase clock is 0. During the evaluation phase, what happens is clock is 1, so PMOS is off and NMOS is on. Now, during the evaluation phase, depending on these input values, your pull down network may conduct or may not conduct. If the pull down network does not conduct, then the output remains to logic 1 because it is not discharging. And if the pull down network conduct, then there is a path from output to ground, and in this case the output goes to logic 0. So it all depends on the data inputs, whether the output will remain at logic 1 or it will go down to logic 0 during the evaluation phase. So this is the operation of a dynamic CMOS logic. Now, the dynamic CMOS logic structure, as in the previous slide, is drawn here again. This is for N-type network, where there is a pull-down network only. A similar structure for a P-type network is shown here. Here we can see, instead of a pull-down network, we have a pull-up network, and output is taken from the in between the pull-up network and the NMOS transistor. This is the output, and this is the parasitic capacitance which is charged during the pre-charge phase. Now let us discuss the issue that occur when we cascade the two dynamic stages directly. In this diagram, we can see there are two dynamic stages which are connected directly. The output of first stage is known as Vout1 and the output of second stage is known as Vout2. Vout1 and Vout2, that we can see. Now, the problem that occur in direct cascading of dynamic stages will be discussed now. See that the clock signal is simultaneously given to all the stages of the network, of the circuit. Now, at the same time, both these PMOS transistors are on during the pre-charge phase, and both these outputs Vout1 and Vout2 will be logic 1 during the pre-charge phase. And simultaneously, when the clock goes 1, your PMOS goes off and NMOS goes on. So, during the evaluation phase, which is occurring simultaneously for both the stages as shown in the diagram, what happens is, here we have taken a case of that in a second stage there is a 2-input NAND gate. Two-input NAND gate circuit is taken where the second input is logic 1. Now, what happens when the pre-charge phase ends and evaluation phase begins? At that time, we see that the output of first stage is logic 1. Now, if this logic 1 is given here and the second transistor has already logic 1, what will happen? Vout2 will start discharging. Vout2 will start discharging. Okay. Now, During the evaluation phase, assume that these inputs are such that this pull down network conduct. If this pull down network conduct according to the inputs, V output 1 will discharge to logic 0 through this path, and it will be logic 0. So, it will change to logic 0, but it will take some finite amount of time for V out 1 to go from logic 1 to logic 0, and during that period your V out 2 fall down to a logic value which may be undefined in nature, because it is discharging, and in that particular time how much it get discharged we don't know. So, this is known as erroneous state. And this erroneous state at the second stage output lead to failed circuits. So, that is a very crucial problem that occur in Vlsi circuits due to direct cascading of dynamic stages. Now, a possible solution for this problem is to use a domino logic. What we do in domino logic is we insert inverter at the output of each stage. So, instead of directly connecting the V out 1 to the second stage input, we are connecting an inverter in between, and the output of inverter is going to the V out 1. Output of inverter is going to the input of the second stage, and this will avoid the problem of erroneous state at the second stage output, because if there is an inverter in between, at the end of the pre-charge phase output of inverter is logic 0, not logic 1, because logic 1 here cause the discharging. If instead of logic 1 we have a logic 0, there is no discharging, and the output of second stage will remain at logic 1. So, there is no erroneously low state. So, that is the advantage of inserting an inverter at the output of each dynamic stage. This is known as domino logic. See here, during the pre-charge phase, when clock is 0, Pmos transistor is on, Me transistor is off, and the inverter output is logic 0. During the evaluation phase, Pmos is off and Nmos is on. Now, if the pull down network conduct based on the input combination, then the dynamic node discharges and the inverter output goes to 1. And if PDN does not conduct, then the node stays high and the inverter output is 0. Now, similar to domino CMOS logic, we have another technique which is known as NORA CMOS logic, or also known as NP domino. This NORA CMOS logic, which is we say that advanced version of domino logic, is designed to eliminate another important drawback of cascading of dynamic stages, that is the race conditions. Here what we do in this is, when we cascade the dynamic logic stages, then we don't only use the NMOS stages, we also use the PMOS logic in alternate stages. This is the first stage will have NMOS, second stage will have PMOS, third stage will have NMOS again, and like that. So there is a pull down network here in the first stage, pull up network in the second stage, then again pull down network in the third stage, and so on. So this NORA CMOS logic is known as the advanced version of domino logic, which is used to eliminate race around condition in the dynamic logic circuits. Here one more important thing that we have to keep in mind, that when one NMOS stage is connected to another NMOS stage, then an inverter is required, and if the NMOS stage is connected to PMOS, then no inverter is required. It is directly connecting. There is no need of any inverter. Okay, and also we have to note that here the first stage work on clock, the second stage work on clock bar. Okay, so when the clock for first stage is low, then the clock for second stage is high. So they work alternately. So race around condition is avoided. So as discussed, NORA introduces alternating NMOS and PMOS logic synchronized by opposite clock, phi and phi bar. Advantages of NORA CMOS: no static inverter is required between the dynamic stages, because there is if the first stage is NMOS, second stage is PMOS, then third stage is again NMOS. So inverter is not required in this case. And it supports pipelining, faster data processing. It reduces the race condition problem, and it is an efficient design for high speed VLSI. Limitations: still suffer from charge sharing and leakage issues, and these can be minimized using zipper CMOS technique, which is another improved version of even NORA logic. Now the zipper CMOS logic, this is advanced version of NORA CMOS. If we see that zipper CMOS is essentially identical to NORA CMOS with the exception of the clock signals. Let us go to the structure. Okay, here we can see that here we have a clock, and here instead of phi and phi bar, we are using psi 1 and psi 2. Okay, so we are using some slightly different clock signals, and why we are using it, that these psi 1 and psi 2 are different from phi and phi bar in a sense that during the logic 1 and logic 0, their values are not equal to VDD and ground. During logic 1, the psi 1 is equal to VDD minus VTP, and during logic 0, it is not equal to 0 logic, it is not equal to 0 volt, it is equal to VTN, the threshold voltage. So what happens is, what is the advantage of having this clock scheme is that during logic 0, your transistor is not completely 0, it is in weak conduction mode. Here instead of logic 0 volt, we are giving VTN, so your transistor is in weak conduction mode. So if there is any leakage problem that is occurring in the circuit, that can be compensated by weak conduction of the transistors. Similarly, here for a PMOS, during the logic 1, PMOS is off. When clock is equal to VDD, but it is in weak conduction when clock is equal to VDD minus VTP. So, if there is a charge leakage problem in the structure here, if there is a charge leakage problem, it can be compensated by weak conduction of this Cmos. So, it will slightly compensate and charge leakage problem can be avoided. So, that is the zipper Cmos logic circuit. This is fine, this is psi 1, slightly less value. Here this is phi bar which is 0 volt, and here it is psi 2 which is equal to VTN, slightly higher voltage. The book that we have taken as a reference is Cmos Digital ICs, Analysis and Design, McGraw-Hill 4th edition, from the author Sung Mo Kang and Yusuf Vlsi. Thank you so much.